All right, hi everyone. Welcome to this section 6.2 video. And in this video, we're going to continue on our journey of using power series to find solutions to differential equations. And in this section, we're going to turn our focus to solutions about ordinary points. Okay, so what are our learning objectives for this section? Well, we're going to define what ordinary points are, and we're also going to define what singular points are. We're not going to utilize that much in this section. That'll be for next section, but we're going to define what it is. We're going to establish the existence of power series solutions theorem. That helps us out a bit in our process for solving differential equations. And then we're going to wrap it all up by solving some second order differential equations using some power series. Okay, so let's introduce what we're going to be talking about this section. So at the end of last section, section 6.1, that video series, we obtained a power series solution to a linear first order differential equation. So just like a y prime differential equation. I think the original equation was y prime plus y equals 0, and we solved it. And so in this section, we're going to move on to more important work. We're going to level up our skills a bit by finding power series of second order differential equations. So we're going to have like y double prime. Okay. And so we're going to find solutions of second order differential equations in the form of a power series whose center is some x value. And that x value is going to be what's called an ordinary point of the differential equation. So why is this helpful? Okay. We're in our introduction to differential equations course, but tons of ordinary differential equations are solvable using this method because coefficient functions, like the one you see down below, a squared of x, y double prime plus a1x of y prime plus a naught x, y equals 0. These types of coefficient functions are allowed to be anything. Okay, so some examples from physics include Bessel's equation, Airy's equation. We're going to check that out in this video series. We're going to solve that and many, many more. So let's begin with the definition of an ordinary point and its consequence, a singular point. Okay, so they're opposing uh, interests. Okay, so ordinary and singular points. So let's consider this linear second order homogeneous differential equation. Okay, so we just looked at this. It's a differential equation with coefficient functions. Okay, and so if we put this into standard form, what does that mean again? That means get y double prime by itself, get it naked. So we're just going to divide everything by that coefficient function a2 of x. Okay, it's some function of x. And so what we obtain is y double prime plus p of x y prime plus q of x y. So does that look a bit familiar? That looks like something we learned in chapter 4, right? So the p of x and the q of x help us determine what is a singular point and what is an ordinary point. Okay, so let's go ahead and define what singular and ordinary points are. So a point x naught is an ordinary point of the differential equation if both coefficient functions p of x and q of x in the standard form that we get y double prime naked are analytic at that x naught. And a point that is not an ordinary point makes it a singular point. So we're throwing around terms like ordinary point, singular point, analytic. Let's just make this a little easier to understand. Okay, so what this method allows us to do is solve for any interval around values that are essentially, we could think about it as nice. By nice, we mean that there are no domain issues at all. For example, dividing by zero, that would cause a domain issue. So the fancy word that we throw around for like nice is the term analytic. So we want the coefficient functions to be nice or analytic around these values. So this is an introductory differential equations course. So analytic, there's more advanced meanings to it as you go deeper into mathematics. But for us, it just means that there's no domain issues while we are in this introduction level. And so, yeah, just domain issues like dividing by zero. So if a value is nice or or fancy analytic, then we call it an ordinary point. Okay, so if there's no domain issues, it's an ordinary point. And so the method today in this section is going to be about finding solutions about ordinary points. Okay, so that's our main focus for today's nice, nice points. Okay, so we're going to learn how to solve singular points in the next section. That's actually a very cool concept, the Frobenius method, and they're not nice values. We're dividing by zero some domain issues. But that's the idea. And so let's go ahead and kind of define what ordinary singular points might be. So we have a couple of differential equations here. Let's see what, ordinary or singular points might be. So we have y double prime plus 3y prime plus 2y equals 0. So we want to see what this might be in standard form, but it's already in standard form. Okay. Y double prime is already naked, already isolated. And so what that means is that 3 and 2 are going to be our P of X and Q of X. So P of X would be 3 and Q of X would be 2. Okay, so these are just constant functions, 3 and 2. So there are no domain issues at all with these. Okay, and so since there's no domain issues at all, this is analytic everywhere. There's no domain issues. It is nice. There's all nice numbers. So analytic everywhere, what that means is every finite value of X is an ordinary point. Okay, and what does that mean? Just means that there are no singular points. Okay, let's look at the next example. So y double prime plus e to the x, y prime plus sine of x, y equals 0. Once again, this is already in standard form, so we don't need to divide by anything. So, we could say it's already in standard form. So it's pretty similar to the problem previously. Okay. And P of X would be e to the x, and Q of X would be sine of X. All right, so not constant coefficients, but now we have actual functions as coefficients. But here, these also don't have any domain issues. Okay, so e to the x and sine have no domain issues at all. There's no x values that give this a problem. So if that's the case, then what happens is we are analytic everywhere. Okay, and what that means is same thing from up above. Every finite value of x is an ordinary point. Okay, all the points are good. All the points are nice. So yeah, no singular points. Okay, so let's move on to example C. Y double prime plus xy prime plus natural log of x, y equals 0. So once again, this is already in standard form. Okay, already in standard form. And so that means x is my p of x, and natural log of x is my q of x. Okay, so once again, we have functions for our coefficients. Um, but we have a problem with the natural log of x. So, maybe let me move this down here. That'd be a little easier to write. So for p of x, there are no domain issues at all for that. Okay. But for natural log of x, there actually is a domain issue with that. So with natural log of x, we are discontinuous at x equals 0. That's where we hit that wall for natural log of x. Natural log can be 0 or be negative. So we hit that wall with x equals 0. So what we would say here is that x equals 0 is a singular point because at x equals 0 we have an domain issue. So that makes x a singular point, makes it a not nice, you know, value. Here I'll say like not nice. Okay, let's try another one. Last one, xy double prime plus y prime plus xy equals 0. Here, we're actually not in standard form. So what we want to do is get into standard form. Okay, so what we want to do is just divide by x to both sides. Okay, so what we get is y double prime plus 1 over x y prime plus y equals 0. Okay, so when we do that, we have that p of x is now 1 over x, and q of x is now, you can think about it as just like 1. Okay, so for q of x, it's just a constant, so there's no domain issues at all. Right? There could be no domain issues with a constant, but for p of x, we're 1 divided by x, and what would make this function undefined? Well, it's undefined at x equals 0. We're dividing by 0 if x equals 0. So that is a domain issue. Okay, so, therefore, x equals 0 is a singular point. So x equals 0 is a singular point. All other x values are ordinary points. Maybe I could say something like that. All other x values are ordinary points. Okay, same thing with question C. Singular point, not nice. All other x are ordinary. points. But okay, so that is a couple examples of kind of establishing what ordinary and singular points are. So hopefully that made a lot more sense than just the theorems and definitions. So that's it for this video, and I'll see you in the next one. Take care.